Hi all, Corey Shipe here. GIS 595 course project. I'm a geologist for the North Carolina Geological Survey. I work specifically on landslide hazards, and so my project is how we can use UAV imagery to supplement our existing LiDAR-based landslide program. So to get on the same page, there's largely two types of mass wasting events that we have in western North Carolina. These can be landslides, such as the Oso landslide from 2014 out in Washington State, image on the bottom left here, showing a very large block of material moving downslope. This is on the order of feet to, potentially feet per day, maybe tens of feet per day. And that's as opposed to debris flows, and in the media this is commonly referred to as a mudslide, but really what we're talking about are these rapidly flowing mixtures of soil, rock, and water. They pick up trees, they pick up all kinds of debris, they travel downslope 30, 40, 60 miles an hour. They can really motor downhill. The example here is from Macon County, North Carolina in 2004. This is the Peaks Creek debris flow. It initiated up here on Fishhawk Mountain, traveled downslope some 2.25 miles, killed 5 people, really impacted the community, and these things really don't let anybody have any warning. So in North Carolina, what we hope to achieve with our landslide program is primarily to understand where they've happened in the past. Okay, that's likely where they're going to happen again. So to do that, we map the historical and recent slide activity and debris flow, and I apologize, but kind of landslide is a kind of a catch-all term. And we do some field mapping to confirm these finds from the LiDAR data, and then we use all that to develop this inventory that can help us model future potential activity that can be hazardous to life or property. So the legend on the right here kind of gives a relative hazard from increasing to decreasing, and this goes from areas where we know that debris flows have occurred in the past to areas where we have that potential. We've modeled that if a rainfall event triggers a mass wasting event, you may have debris flows form in these channels, and compare that to areas where we have historical deposits, but maybe we don't have any information to suggest that there is an active or potential threat. And then we have these areas that are great. Okay, they don't give us any indication that we're going to have any landslide activity in that area. And so there are a few challenges with this. You know, we start off with LiDAR data, and in North Carolina, thankfully, we're very lucky to have sub-meter LiDAR data now, but the initial landslide program in North Carolina was conducted with the 6-meter legacy data that probably most of you are familiar with. So some of the challenges, okay, it's easier to map a landslide versus a debris flow. And looking at that kind of in a different way, it's easier to look at a hill slope versus a drainage channel, which is where debris flows typically occurs in these drainage channels. So here's an example. This is some of the new sub-meter LiDAR data. The colors represent slope. The purples they're the very steep slopes, and the blues and greens are gentler slopes. So this is an area in Polk County, North Carolina, not far at all from where I'm making this recording here. This is called Little Cove Creek in the Green River Game Lands. And just on this one example, you can see a landslide, and there's actually several in here, but if you can follow the cursor kind of outlining one of the larger landslides where we have a hill slope failure, you can pick out another one kind of over here, and kind of the more we look, the more we can pick out some of these anomalous hill slope features that represent landslides. But what is less obvious is this channel right here, which I can tell you from visiting in the field and being out there, it is a debris flow pathway. It is an area of repeated historic debris flows. You have boulders and debris embedded in the soil as far as you can see down, which in some cases this channel has incised 10 to 12 feet of soil and debris that you can see. So it's been going on for a long time, but there's not necessarily anything in the geomorphic record here to suggest that, or I'm sorry, in the LiDAR data to suggest that we should be concerned about this channel. So another challenge and related to this is field mapping. Okay, so field mapping, well, typically we have to do this all year long. We have a lot of work to do, and so during leaf-on conditions, hurricane season, which is when we have the most landslide activity in western North Carolina, it can be very difficult to map during these leaf-on conditions. You can see so much more between the months of November and March here in western North Carolina. And then also just the scale. We are tiny little creatures on this planet, and we really cannot see a lot from the ground as opposed to from the air. So here's an example. This is a photo I took last week of an active landslide site. I am standing on a debris flow track looking south. The map on the right, again, this is some of the sub-meter LiDAR data. This is oriented north up. And the yellow arrow here points to a kind of an anomalous feature. This area with inconsistent slopes is a debris flow track, and we picked that on the LiDAR based on kind of training our eye and looking at it. We went out in the field to verify it, and sure enough, it was a debris flow track. But so this is something that would be difficult to figure out in the field. We can figure it out from LiDAR data. It's great. All right, so but a potential solution to kind of wrap these challenges up is using UAV imagery. So there's a number of advantages. Primarily, it's cost effective, but I think primarily the advantage is that we can deploy a UAV, we can capture data minutes, hours, days after a large landsliding event. The imagery on the right was captured with a UAV following the May 2018 Polk County storms. Sorry to be what's the word here? The woman in this house here died. This was a casualty from those storms, and it's unfortunate, and it's kind of what motivates a lot of our work are these casualties. These are coalescing debris flows that befell this home in the Pacolet River Valley last year, and these images were captured with a UAV days after the event. The processing is rapid. The orthomosaic it creates, 3D model, those are kind of the two primary end goals we have with this data. So from that, we can capture the extents to a very accurate degree. We can get the extents of the slides, we can get the volume, how much material actually moved, and then we can also do repeat monitoring. Not all mass wasting in North Carolina are these rapid debris flows. Remember, we've got these slower moving landslides, and so I'll talk about one at the end here, a large slow moving landslide we have that it would be great to do some repeat monitoring. So let's get into the business here. So the case study, this is using some imagery from Puerto Rico. One of my NC State colleagues is now a professor down at the University of Puerto Rico, and in 2017, Hurricane Maria made landfall, Cat 5, very large storm, thousands of landslides, debris flows, a very devastating event for the country. And one slide in particular was imaged amongst others, but I've got the data for one slide in particular, one debris flow, I should be clear. So 125 RGB images, geotagged JPEGs collected in March of 18, so about 7 or 8 months later. And this was DJI Phantom 3. There were 2 ground control points. I think this was one of Dr. Hughes's first efforts here with the UAV. And so there's only 2 ground control points, and they are kind of close together. So the georeferencing has a little bit of to be desired. Here are a few example photos of what they picked up. So what I did with it is I processed the data in Agisoft to Metashape, generated a 3D point cloud, orthomosaic, exported these as a geotiff and as an LAS point cloud of that resulting DSM. So that LAS file just gives me a little bit more flexibility in further processing. Here are kind of some screenshots of the perspective view of the result. And here's the orthomosaic put atop some base map imagery in ArcGIS. So within ArcGIS, I take that LAS file, interpolate that into an elevation, hillshade, slope rasters, can kind of can clip it, can do what I need to. Combine that with some USGS published 2015 1 meter LiDAR. So this is pre-storm, this is beforehand, and you can see it on the bottom left here. And my kind of idea here was, okay, let's digitize the debris flow extent and let's see what we can figure out. What do we now understand seeing that data in context? And so the DSM on the right here, this is just put right atop that 1 meter LiDAR DEM, so you can see a little bit of georeferencing issues here. And that's probably where it shows up most, but they do exist. So my question again is, okay, what area failed, and do we have any historical precedents? If we were doing this method where we begin with the LiDAR data and we look for these areas of historical failure, what may we have found? So on the left here is the 1 meter USGS pre-storm LiDAR DEM with the slope map on it. And on the right here is that same hill shaded DEM, but it is now just got the imagery just for the debris flow track itself posted on it. So if we do this method, we actually can find some historical slides, which I thought was really cool. So they are out here, okay, right at the initiation zone, which the debris flow typically gets kicked off by something. So something happens at the head is what it's called, the top of a debris flow, to kind of initiate that process. And then generally it just picks up speed all the way down the drainage channel. And it looks like that's not unlikely. I mean, that is reasonable in this case, where we have at the head of this, we have these historical failures. And I'm going to go back to the previous slide just for a moment so you can see what I'm talking about. And what we're looking for are these arcuate shapes, these arcuate head scarps that represent historical failures. Okay, and so if I look at the rest of the DEM, I can find these elsewhere. Okay, I find some relatively large ones. I find some here to the west that are likely associated with some other drainage channels and not this main failure plane. But yeah, so this is great. I was really psyched to see this. So what challenges did I have here? There were several. Again, the georeferencing workflow, and that may be rectified just by having some more GCPs and having better distribution of those. I also think that just having a better understanding of georeferencing a LAS file, so I was able to to adjust the georeferencing of the geotiff, the orthomosaic, but I was not able to figure out how to georeference an LAS file, so that would be helpful. Another, leaf on season and debris flow in the track and structure from motion. So how do all these things play in? Well, we're talking about a landslide. It is going to have a lot of exposed soil, but it's also going to have a lot of trees, a lot of garbage, not garbage, but a lot of detritus. It's going to have a lot of organic material in that slide track, and so that can present challenges for structure from motion, even on a recent slide event. Smooth fusion, I think, would be great. So if I can figure out the georeferencing, then going to a smooth fusion methodology for bringing these DEMs, the existing pre-storm DEMs in with these repeat survey DEMs will help out a lot. Unfortunately, with our assignment just this week for smooth fusion, I didn't have time to wrap that into this. Additionally, batch processing, I have an idea for a few Python tools to generate a little toolkit that can maybe expedite this workflow in the future. And then local sites. Okay, that's kind of the big next step here. This photo is a slide very close to where I am. It's obviously this road is closed. Slide direction is in the to the right on the photo here, which is to the south. And this is what we call a big slow mover. This is a landslide that is moving slowly. We're talking on the order of inches to feet per month. And so repeat surveys here would be extra helpful to correlate with rainfall data or climatological conditions and understand what is triggering the motion on this slide. So that's what I've got. This class has been great. So I hope everybody else enjoyed it and hope you enjoyed this talk. Thanks.